Hello, good morning. Good morning, everyone, for this event on novel missions enabled by electric propulsion. My name is Marco Molina. I am the Managing Director at CETAL for products and sales. And I'm very glad to welcome the panelists, the speakers, and the chairman of this conference that CETAL is very proud to have organized together with Politecnico di Milano. These days, we have been very much excited by the new achievements in the heavy lift rockets and for space tourism. All the people in the world are now aware that access to space is possible with rockets, also for every people, for non-professional astronauts. But as soon as we are in orbit, so after the first mile has been done, it is time to start the real space flight. And this is where electric propulsion can be really a game changer. In this conference, we will have a deep dive into the available technologies related to electric propulsion first, and then we will understand how these low thrust devices can enable a variety of missions, not only around the Earth, but all over the solar system. This is really what we mean by space exploration and a new way to sail through the planets and through the solar system. I'm very glad to introduce you the next speakers. There will be two blocks in our morning. The first one will be about electric propulsion. We will have a presentation by CIRA, by T4I, by CETAL, and then we will move to the astrodynamic session. That is where the variety of missions enabled will be presented, and we will have speakers from Politecnico di Milano and Politecnico di Torino. I'm very glad to European Space Agency that supported us providing the chair people for the first two sessions, and I'm very glad to Italian Space Agency that allowed the chairman for the panel to be present and animate what is going to be the final discussion and the wrap-up. We are ready to start. It is going to be quite a dense morning, and I'm very glad to leave the floor to Kathy Dennenmeyer. She's an MS in aerospace engineering from the University of Stuttgart, and then a PhD in plasma physics from the University of Orléans in 2012. Since 2013, Kathy is working as electric propulsion engineer at ESA in the electric propulsion department. Kathy, the floor is yours to introduce the session, Electric Propulsion Technologies. Enjoy and thank you.
Thank you. Good morning to everyone. I'm very happy to be with you this morning to lead you through the first session on electric propulsion. So unfortunately, all the audience is connected via YouTube, so we won't have the possibility for you to ask questions directly. But if you have any questions, don't hesitate to send them to the organizers of the workshop. So just use the email that you've used also for the registration, and the organizers will make sure to transfer your question to the relevant speaker and to make sure you get your answer back. I hope that this is clear for everyone. And then I guess we can immediately start with the first session. So it's on electric propulsion. It will give you an overview on nano and macro satellite propulsion, but also space exploration, and to show a bit the vast capabilities that electric propulsion can offer for space propulsion. So I'm happy to introduce to you the first speaker. The first speaker is going to be Daniele Pavarin. He graduated in mechanical engineering in 1997 and defended his PhD in mechanical measurements at the University of Padua in Italy, developing a hypervelocity impact facility in 2001. He was visiting scientist at the Oak Ridge National Laboratory in the US in 1999, and he is now Associate Professor of Aerospace Propulsion at the University of Padua. He's also the founder and CEO of T4I, a spin-off of Padua University, developing advanced propulsion systems for microsatellites. And he's going to talk to you about electric propulsion for nano and microsatellites, and more in detail give you an introduction of the Regulus propulsion system. Daniele, the floor is yours.
Daniele, please unmute yourself. Thank you.
Good morning to everyone. Thanks for introducing me. It was a great honor to be invited to this session, where we do small propulsion system. Thanks, it's have a possibility to introduce what you do here. We are very glad. So T4I is a company that started its operation in 2014 as a spin-off for University of Padua, and aiming at introducing into the market the research done by my group, who started doing this type of research in 2006. My group was focused on developing innovative propulsion system specifically for microsatellites. Activity developed through electric propulsion and chemical propulsion mainly, and the focus again was to design and develop systems capable of dealing with the specific need and specific challenges microsatellites provide. What you can do with a motor, it will be subject of the following session. However, of course, you can do a lot of things, and you need a motor to do a lot of things around the Earth. Without a motor, a satellite is basically a dead object. So, of course, it can provide some commercial operation, but it's very limited. When you put a motor on a satellite, it becomes capable of doing things that can satisfy different type of markets. So a motor is a very important asset on board a satellite. Our company, as I was mentioning before, operates in both in access to space and movement into space, and in space propulsion system. We do develop an electric propulsion system. We do develop micro motors for satellites as cold gas monopropellant motors and bipropellant motors. And we also do develop a hybrid rocket motor specifically designed for access to space. Referring to electric propulsion system, our first product is Regulus. Regulus, the concept of Regulus started in 2006. The idea was to develop something easy to be used by a satellite. So at that time, where microsatellites were at the beginning, we questioned ourselves about the need of future microsatellites. And we do recognize that they will need something simple to manage and to operate. So that's where Regulus comes from. The principle of operation of Regulus is pretty simple. As you can see here, you have a reservoir injecting gas into a discharge chamber, and then the discharge chamber is surrounded by an antenna and electric field. Plasma is ejected directly into space, providing thrust. This is what you see when the motor is operated. The elements that make Regulus different from other propulsion systems are that it doesn't have electrodes, it doesn't have neutralizer. And so it is able to operate with different gases. As you can see here, you see operation with xenon, you see operation with iodine. It can operate with multiple gases, providing a lot of versatility on what you can do with this motor into space. So as you have seen in the picture, it has several this motor has several subsystems. So you start from, and it's a box. is a box that is interfaced with a spacecraft. When you have several subsystems, all of them has been developed internally, all of them, but the power control unit that for the moment is just buy from an external provider, but all of the other subunits which are critical for the motor have been specifically designed for the specific need of this type of motor. So the class of power is 50 watts. As we considered this one of the specific power that you can find for satellites in the range between 6 and 12 U. You can see here performances of a motor, and then specifically you see that it's a box. It's 1.5 U, and is designed to be easily connected inside of a satellite as a box. You just need to plug it to put the IT cable, the power cable, and the motor start its operation. I would like to stretch one of a specific feature of this motor, which is the capability of working with iodine propellant. Iodine, it's a very interesting propellant for us because it's a solid state, so you can store it in the propulsion manufacturer, in the premises of a propulsion manufacturer, and then you can deliver the motor, which can be easily operated since iodine is confined inside of its tank, not pressurized, so it doesn't provide any safety aspect to the satellite integrator. More you see that the tank is a square tank, is a cubic tank, is not rounded, so it has a very high volumetric efficiency, and this is because iodine is not pressurized, and then the iodine is very dense, so you need a very small volume for a pretty high mass of propellant, which make it very interesting to have optimize the volumetric efficiency of the motor. One of the critical aspects of microsatellites is that they are very dense. If you compare a big satellite respect to a small one, you see that a small satellite is much dense than a big one. And so volumetric efficiency is a very critical aspect. So iodine is very interesting for these two aspects. And it's supposed to make the life of a satellite integrator much easier, since you need not to operate with something that is pressurized or something that need to be filled close to the launch pad. I would like just to stretch what are the specific aspects of this motor. If you look at the performances, the motor has lower performances as electrostatic propulsion system, as ion and Hall effect thruster. What we used to say is that if you need a Ferrari, you do buy a Ferrari, but of course you have to pay a Ferrari. But if you don't need a Ferrari and you need a 500, and the 500 it's enough, and you want to spend the money for a 500, this motor is what can fit for what you need. And why? So one of the aspects that it's crucial is the cost to performance ratio. The reason why this motor is less costly than other motor are related to its technical feature. As I was mentioning before, you do eject a plasma. So what you eject is a neutral plasma, and you don't need grids, you don't have electrodes, and you don't need a neutralizer. So you have less components respect to other propulsion system, which make the system simpler and then at the end of the story, less costly. The fact that you don't have components as grids or neutralizer make the motor suitable of operating with different gases, so it makes it more versatile, and it reduces the aspect related to life to operational time. So it makes it also suitable for long-lasting mission. The tank is an external tank that can be sized for different needs. For the moment, we the current size of a tank allow 3 kilonewton per second total impulse. It can be, we are designing a bigger one for 11 kilonewton second total impulse. The technology is robust in the sense that it's composed by few components, and in this sense it's robust because it's simple. The story started in 2006, as I was mentioning before. We went through several engineering models, and then we went through, we developed a bigger motor on which we learned a lot in cooperation with Thales Alenia Space. It was a 400-watt motor. Then we started developing subsystems, electronic subsystem, gas fluidic subsystem. And then in 2018, we arrived with a full-scale laboratory model. In 2019, we developed the qualification model, and then now Regulus is in space and is integrated in a satellite, and we are in a commissioning phase. We did, of course, all of the tests needed in order to qualify it. We did also some special tests when I'm sure Sabina will mention later, in cooperation with Polytechnic of Turin. And we had the possibility of assembling our motor inside of our satellites, and so we could make some tests inside the vacuum chamber with operational motor with a mock-up of the real satellites. And then finally, the system has been launched on March 22 of this year on board of a Gauss dispenser, and it's currently in the commissioning phase. So we are making several operations in order to verify system operation in space. The system was launched on board of Soyuz. I will end my presentation saying that the electric propulsion system is the core of our activity. It's one of the core of our activity, but we do develop also other propulsion systems. And the idea is that a future platform will surely benefit a lot by electric propulsion system, which will be an enabling technology. However, we do consider that the need of future platform will be different, and they may need a different other propulsion system all combined together, and capable of talking also with electric propulsion system. So all of them put at system level, capable of operating all together for the benefit of complex mission. That's why we don't do only electric propulsion system, but we do also chemical rocket, cold gas, and of different size to cope with the need of future missions. So thank you. That's the end of my presentation.
Thank you, Daniele. So I don't know if one of the other speakers would like to ask a question now, then, because we have some time. Otherwise, I have a quick question for you. So you have already
Yes, sure.
You already have the first Regulus system in space, and can you say a bit more about the performance you measured? Is it similar to what you expected from your ground measurements, or do you see any difference? Or
I was saying that we are still in the commissioning. The satellite is still in the commissioning phase. So the satellite has to complete its commissioning phase. It was a little bit longer, but we did expect. So we don't have yet performances.
Okay, but so you didn't even try to ignite it yet, or you have?
No, the motor is,
okay.
The satellite is still in commissioning. So we have still to wait to turn off the motor. We did the communication with our motor, and everything was fine so far. But still the satellite has to complete some operations.
Okay. Does anyone else have a question, or? Then for maybe Marco, is it okay if we continue directly, or should we stick to because we're a bit ahead of schedule, but
No, I think we are sharp on time.
Okay. Then I guess we just continue
Yes, please.
Okay, perfect. Okay, so then let me introduce to you the second speaker of today. So it's going to be Tommaso Misuri. He graduated in aerospace engineering in 2005 at the University of Pisa and received a PhD from the same institution in 2009, defending a thesis on plasma acceleration mechanisms in electric propulsion. He has today over 15 years of experience in space propulsion. He was first working as R&D engineer and then as project manager, and today he's the head of the propulsion division at CITEL. And Tommaso is going to give you an introduction on electric propulsion for space exploration. Tommaso, it's all yours.
Thank you, Katha. Thank you so much for the introduction. I'm super happy to be here, and I'm happy also if I have a few minutes more, if we are a little bit ahead of schedule, so I don't have to rush too much. Tell me if you see my screen. You see it?
We can see it. Perfect.
Good. So I will start with a quick introduction about electric propulsion for space exploration, and then Tommaso Andreyusi, after me, will delve a little bit deeper into the technical problems that comes with electric propulsion for space exploration. So the first question is, which kind of propulsion we would like to use for space exploration? And while wondering this, I was imagining to be in a period where electric propulsion wasn't there, which is not much difficult. Actually, recently, it happened to me to download a huge document from NASA. It was a technical memorandum dated 1966, which was describing in detail all the future Apollo mission. At that time, of course, the mission was still to happen. And the whole document is a sort of Bible for system engineering. It deals about everything: re-entry, guidance, control, selection of landing sites, almost everything. But the striking thing is that the very first topic that is faced in this document, I repeat, it's 700 pages. The first 30 pages are devoted to study the energy requirements for lunar landing mission. So it's a matter of answering a simple question: how much propellant do we need to land 2 men on the moon and bring them back, of course? So, and what we see is that actually Saturn V was able to bring in low Earth orbit 140 tons. And then from there, from low Earth orbit, all the in-orbit operations started, with the final objective of landing men on the moon and bringing them back. The mass of the lunar module ascent stage was about 2 tons. And the result is that about 100 tons have been used as propellant. So 100 tons in the mission were propellant for in-orbit operation. Of course, this is an unfair example, because there you have a manned mission. Time was a constraint. It's not a super simple example. It's one of the most successful missions of all times. But I mean, part of the spacecraft was jettisoned along the way. You have different motors. But even if you simplify this as much as possible, and you assume to have an ambitious exploration mission with a delta V of about 10 kilometers per second, this is a ballpark figure. Of course, exploration missions always have a quite high delta V. Well, in this case, if you use chemical propulsion, let's say with a specific impulse of 300 seconds, you will end up with having a propellant mass fraction of 95%. So the final mass left is about 5%, and its structure, payload, and everything. If you can use electric propulsion, the propellant mass fraction dramatically drops, and you have a lot of mass left for all the rest. If you have to bring provisions, robots on another celestial body, it's necessary to use electric propulsion. This is an enabling technology. If you don't have a manned mission, so time is not a constraint, using electric propulsion allows you to bring to the final destination a much higher mass. Now, this is a very quick introduction, but now what we need to make sure that in the near future, we will be able to use electric propulsion for space exploration. I'm focusing on the 3 destinations that we all have in mind in this period when we think to space exploration: the Earth, Moon, and Mars. And I will try to point out some important synergies, also in the light of the developments that we are currently pursuing at CETEL. So let's start from the Earth region. There is a region, a thin region around the Earth, between 180 and 240 kilometers of height, that is almost unexploited, because you cannot put a satellite there because of atmospheric drag. So atmospheric drag at that altitude will drive down your satellite in a matter of days. So the only way to keep a satellite at about 200 kilometers of altitude is to use a novel electric propulsion system that is working basically breathing the air around the spacecraft. So this is the so-called air-breathing electric propulsion. And there are immense challenges in developing such a system, not only the propulsion system, but the whole spacecraft. And the idea here is to collect the particles of the upper layers of the atmosphere, accelerate them, and generate a thrust that can counteract the drag and maintain the satellite into orbit. And this allows us to explore this unexplored region around the Earth. But there is another benefit of the study that we are carrying out about these propulsion systems. The propellant is mostly made of oxygen, and oxygen is a really hostile propellant. It reacts with everything. It's a little bit more difficult to ionize with respect to the traditional propellants that we use in electric propulsion, like xenon and krypton. But it's also a propellant that we can find on other planets, on other celestial bodies. If you go to the moon, you can easily find that 42% of the regolith is made of oxygen. There is water in the form of ice that can be, by electrolysis, divided into hydrogen and oxygen. And if you can use efficiently oxygen as propellant, you can retrieve the propellant for your future missions in situ. So this is the special relevance of what we are doing for a mission which is intended to operate around the Earth for other missions that in the future could aim at the moon or at Mars. But of course, this is a little bit far. So at the moment, to go with a cargo mission to the moon, what we need is to operate thrusters with a very high power level. We are developing a 20 kilowatt thruster, which is capable of providing a thrust of about 1 Newton. 1 Newton is, of course, a very low thrust for a chemical propulsion system, but is a huge thrust for an electric propulsion system. And if we have sufficient power with such a thruster or a cluster of such thrusters, we can reduce the transfer time and efficiently use propellant for moon missions. If we move to Mars, here, what we would need is to have a higher specific impulse. The delta V goes up, and it's important that the thrusters work at an operating point where the propellant consumption is lower, so the specific impulse is higher. And what we can do, we can use the same baseline, the 20 kilowatt thruster, but we can operate it at higher applied voltages and with a different propellant, specifically krypton. So with these two slight modifications, we can achieve specific impulses which are as close to 3,000 seconds, and with a decent amount of thrust that can allow us to move from the Earth to Mars in a reasonable time. Of course, reasonable for robotic or cargo missions. If we are talking of manned missions, we need chemical propulsion. Now, I close with this slide and then leave the floor to Tommaso to better deal with the topics that I have mentioned. There are really many challenges in developing electric propulsion systems for space exploration. I have reported some of them here. We are not only studying the thrusters, but we are also studying the complete propulsion system and sometimes the complete spacecraft system. So we need also to handle the power that comes from solar arrays. So there are possible architectures that are novel architectures that are under study, like the direct drive architecture. We are exploring the possibility of having a better distribution of power in order to be efficient, even when many kilowatts are coming to the thrusters. We are exploring the possibility of doing a clustering of different thrusters for complex missions. This was also addressed by Daniele in the previous presentation, and it's very true. Complex missions will need both electric and chemical propulsions, because they are probably going to experience very different phases with very different maneuvers. So sometimes they will need a high specific impulse, sometimes they will need a high thrust to finally control the spacecraft. And I leave you with pictures coming from two experiments that have been carried out recently in our facilities, and these experiments, as many others that we are carrying out right now, are experiments that are world premiere. It's the first time that in the world we are testing these specific technologies. On the left, you see the air-breathing electric thruster. On the right, you see a magnetically shielded 20 kilowatt thruster, which we have tested for about 2,000 hours with krypton as propellant. And some of these hours has been done in direct drive configuration. And with this, I close my presentation. I hope that time was fine, and I leave the floor to Tommaso, which will continue basically on the same path.
Thank you, Tommaso. So then we go
sharing. Yeah.
We switch from one Tommaso to the next.
Yep.
So the next speaker is going to be Tommaso Andreyusi, who defended his PhD at the Scuola Normale Superiore in Pisa in 2008, focusing on the following years on the theoretical modeling and experimental investigation of plasma thrusters. Since 2015, he's the director of CTEL's EP technology development team, and he's responsible for the design, the development, and the qualification of electric propulsion systems. He also supervises R&D activities on electric propulsion with a specific focus on high-power Hall thrusters, air-breathing electric propulsion, and plasma diagnostics. He is the PI of several programs funded by ESA, ASI, and the European Commission. And today, Tommaso is going to talk to you more on the use of electric propulsion for space exploration, giving you insights on the relevant technologies. Tommaso, it's your floor.
Thank you very much for the introduction. I will share my screen. Okay. I'm really glad to have the opportunity to present today the activities that we are carrying on in CTEL to develop electric propulsion in order to enable novel mission scenarios. I will try to give you more details about the activities that Tommaso Misuri introduced, and I will start from a simple consideration related with existing electric propulsion concepts. At the moment, one of the most interesting concepts, one of the most developed is the Hall thruster. And this is related with historical reasons, but also on the fact that electric propulsion system based on electrostatic acceleration, like the Hall thruster, are able to provide very high performances in terms of specific impulse and thrust efficiency. And this is really a key feature for space exploration and also for space transportation. Because as Tommaso described so clearly before, the possibility to have a very high specific impulse implies a very sharp reduction of the propellant needed to achieve a mission. So even if this technology, the whole trusted technology or the grid ion engine technology is nowadays already commercially exploited, there are several research and development areas in which we can push the limits of this technology to allow for novel missions. And in these areas are the topic, let's say, are the focus of my presentation today. And are mostly related with the scaling of such propulsion system to very high power level. There is also a great interest in the recent years to go to very low power levels. And I'm sure that in this morning there will be a further discussion about the possibility to have constellations in the low Earth orbit. But for space exploration, very high power will be needed to realize the missions. Another key research and development area is the one related with the increase of trusted lifetime in order to allow for long duration missions to Mars, for example, or in the cislunar orbit. And I will describe also activities related to the simplification of the power architecture, again, to increase the efficiency of the overall system. And I will close my presentation with an overview on the use of alternative propellants and with a specific focus on air breathing operation. So you can see here that we did several testing with different propellant already. And one of the main reason to develop electric propulsion, as described by Tommaso, is the possibility to reach the moon and to go beyond. And in this slide, you can see an artistic impression of the power propulsion element that NASA is developing together with Maxar. And it is evident in this image that the core of this propulsion element, which represents the main module of the future lunar gateway for the exploration of the moon and for the installation of a new space station, the cislunar orbit. The core of this element, as you can see, is the electric propulsion system that is based on high power Hall effect thrusters. You can see there are in this module 4 6-kilowatt Hall thrusters and 2 Hall thrusters that are above 10 kilowatt of power level. And high power Hall thrusters really represent a precondition for the expansion of space exploration and for the possibility of transportation of cargos to the moon or to other planets in the solar system. Even if this is really a critical technology, and even if there are several thruster prototypes that have been developed in the past years with power levels that are above 10 kilowatts. Today, there are no qualified thrusters with such power level that can be used in flight. There is an exception, and it's really the one that you see in this picture, and it's the Aerojet AEPS thruster that is currently being qualified by NASA and Aerojet Rocketdyne. But except for this, no other system of this power is actually available. So what is the reason that we want to use a high power Hall thruster? Some of these reasons were already described. The idea is that with the very high power Hall thruster, we can produce thruster level larger than 1 Newton and we can also reach specific impulses larger than 3,000 seconds. Hall thrusters are really a key technology for exploration and transportation because they can produce high thrust and high efficiency operating with xenon. And they are really a reliable technology, a robust technology with a long flight heritage. But they can also reach very high specific impulses, reducing the mass of propellant if we operate with krypton, which has also the advantage of having a low cost with respect to xenon. And then there is another key feature that is very important, and it's specific of Hall thruster technology, that this thruster has a very large thrust to power ratio. So they can produce high thrust with a high efficiency at a relatively low voltage, discharge voltage. And this can allow for a great simplification of the power architecture when we consider direct drive architecture. I will describe later what is a direct drive architecture, but it is really another game-changing technology for space transportation. So if this is true, so there are several reasons why we can use, we should use high power of thrusters. Why there are no qualified thrusters available of this power level? Because there are several challenges, of course, associated with the qualification of these propulsion systems. And the main ones are the severe requirements that the propulsion system should comply with in terms of, first of all, lifetime. So this system should work for 10,000 hours of operation and more. A very high power Hall thruster, in order to be really an enabling technology, should reach more than 30,000 hours of operation to allow for very complex missions. Then there are requirements related with radiation, with environmental conditions. And one that is very critical is the possibility to operate in a very large range of conditions. And then there is the second challenge, and this one is really probably the major showstopper for qualification, and it's the cost and duration of the testing process. In order to develop very high power Hall thruster, you need big facilities, and you need a very long time. So very few companies worldwide have the capability to develop such a system, but CITEL is among them because of a long heritage in the development of Hall thrusters, and also because of the availability of the IV-10 space simulator, one of the largest facility in the world and the largest in Europe for the testing of electric propulsion. So thanks to these two advantages, we started the development of a 20 kilowatt class Hall thruster in 2015 in the framework of an ESA technology research program. And we performed since 2015 several design iterations, starting from a traditional architecture, a traditional design of the thruster. We were able to assess the erosion of such traditional thruster design in 2017, performing a 150-hour wear test for the first time in Europe. And based on the outcomes of this first test, we decided to investigate different magnetic configurations for the improvement of the thruster lifetime to reduce the erosion of the thruster due to the plasma. Then we investigated the influence of cathode configuration, and we at the same time upgraded our facility, because during the development activities we understood that in order to carry on the development and qualification of the thruster, we would need very high pumping capability, because this is clear for every people working on the electric propulsion field. When you have to test the thruster, you have to do it in vacuum, and you have to maintain a very high vacuum level when you are injecting the propellant in the chamber through the thruster. And when we talk about the 20 kilowatt Hall thruster, we are talking about a lot of propellant, a lot of mass flow rate going into the chamber while the thruster is fine. So we developed several prototypes in the past years. We upgraded the facility in order to test them, and we developed also specific diagnostic tools to characterize the thruster. And the design, of course, was not based only on the heritage of the different models of the 20 kilowatt thruster, but we could also exploit activities on the HT5K, which is our 5 kilowatt class Hall thruster. You can see here that we did in the past years, we did a different test campaign in order to improve, as I was saying, the lifetime of the thruster, changing the magnetic field. You see in the top picture two different magnetic configurations, and it is possible to notice that in the right one, the plasma is a bit detached from the wall, and this is thanks to the magnetic field, and can really increase significantly by order of magnitudes the duration of the thruster. And in the bottom picture, you can see testing done with the different propellants, in particular with the different mixtures of xenon and krypton to characterize the effect of this different propellant on the operation, the performance, and the lifetime of the thruster. So thanks on all these activities, we were able to define a new configuration of the 20 kilowatt thruster with magnetic shielding, so with an increased lifetime, with a centrally mounted cathode, and compatible with operation with different propellants. And thanks to the Horizon 2020 Chaos program, we were able to start assembling a complete propulsion subsystem. So we focus not only on the thruster and cathode, but also on the integration of thruster and cathode with the platform, together with a flow management system and a power architecture. And we derived requirements for the system from very ambitious exploration and transportation scenarios, like those presented before my presentation. And we targeted a very long lifetime and a high robustness of the system, as well as a simplification of the architecture. And you can see here the outcome of these trade-offs. And one of the key features in this system architecture is related with the managing of the power. The managing of the power is what we call the direct drive architecture. And so what is a direct drive architecture? You can see here the picture of Space Bus Neo, that is one of the high-power geostationary platform developed by Thales France. And we are collaborating with Thales France to develop an innovative architecture that is called direct drive in order to simplify and to increase the efficiency of power conditioning and utilization on board of spacecraft. So in basically the direct drive electric propulsion system corresponds to a direct and non-isolated connection of the solar arrays to the electric propulsion. So basically we are removing the power processing unit that regulates the power from the voltage of the bus in the satellite to the discharge voltage of the thruster. And by removing this element and by using all the power available, in particular when we know that most of the power will be dedicated to electric propulsion, we can reach a global power efficiency up to 98%. And this is not only a matter of efficiency of the power processing unit, it's a matter that when we have a satellite like the Space Bus Neo, at the beginning of life, we will not be able to use all the power available because the system, the propulsion system is designed to, and the power system of the spacecraft is designed for end-of-life conditions. So at the beginning, we have a loss of power simply because we do not extract all the power available from the solar arrays. Then there is a power loss in the power conversion unit and the power loss in the power processing unit, which implies an overall losses for traditional system up to 16%, which is really a great difference with respect to a direct connection of solar arrays to the thrusters. If we can increase the efficiency, removing all these intermediate steps, we are able to reduce significantly the cost and mass of a platform. And this is really critical when we talk about exploration mission and transportation. So what are the challenges? The challenges are related with the lack of galvanic insulation of a direct drive electric propulsion system, the interaction between the solar array and the thruster, which are directly connected, so there is no regulation in the middle, and the low technology readiness level of high voltage solar arrays, which are needed if we want to operate the cluster at 300 volts. So several activities are being performed by CETEL starting from 2013 and are still ongoing in collaboration with Thales France and thanks to several Horizon 2020 programs to improve the maturity of a direct drive architecture. I will present a bit more in detail the world premiere that Tommaso anticipated. At the beginning of this year, we were able to perform in our IV10 facility a system test of our 20 kilowatt thruster operating with Krypton with a direct drive operation coupled with the flow management system. And we operated the system for 300 hours in this configuration. while the thruster itself accumulated more than 2,000 hours of firing time. And these activities are not closed. We will continue the development of the high-power propulsion system in the framework of the Aspire program that started at the beginning of this year, and that will try to design a roadmap for the qualification of the system, pursuing also the modeling and the development of an alternative qualification strategy to reduce the risks associated with this complex qualification process. I hope that I still have a few minutes to introduce the second innovative technology that we are developing in CTEL, and that is the one that Tommaso introduced first. So when we want to go close to the Earth, we have to completely change the approach with respect to the Moon or Mars. If we want to go in that layer of the Earth atmosphere, where nowadays is almost impossible to have satellites, it's almost impossible to explore. So between 180 and 240 kilometers, we need to develop air-breathing propulsion. And air-breathing propulsion is basically a propulsion system that collects the particle of the atmosphere, the same particle that will generate the drag and that will make the spacecraft fall on the Earth. We collect those particles and we ionize them and we accelerate them with electric propulsion. And in this way, we can counteract the drag and keep the spacecraft flying at very low Earth orbits. So why we should use air breathing? So why we should do all the, we face all the challenges?
Tommaso,
yes.
Can you try to quickly wrap up because we're a bit behind? Sorry.
Yes. No, yes, sure. So I will just summarize the challenges of air-breathing electric propulsion. Air-breathing electric propulsion is a very complex technology because we have to develop technology for the ionization of air. We have, which is a very hostile propellant, but also we have to find a way to collect the particles in front of the spacecraft. You can see in this slide the white object in the front of the spacecraft is what we call the intake. We have to collect the particle, we have to compress them in order to give to reach a good ionization, and then we have to accelerate. And one of the main challenges, besides the development of this critical technology for collection, ionization, acceleration, is that the system is really related with platform design. The drag and the collection are related with the overall architecture of the platform, and this is one of the main challenges. And the second challenge is that it's really difficult to test on ground such a system because we have to reproduce a flow reaching the intake with the orbital velocity of the spacecraft. So something around 8 kilometers per second of oxygen, atomic oxygen, and molecular nitrogen. So just to give you a brief summary, this is what we need to make in order to produce a working air-breathing propulsion system. We need to generate a thrust that is higher than the platform drag, and we need to collect, ionize, and accelerate the atmospheric flow that is in front of the spacecraft during its orbit. Okay, I think that I will just skip this part to conclude with the summary of what we did in the past years in CETEL. So we were able to perform a system test on ground for a RAM-EP concept, so air breathing electric propulsion. We reached a good ionization capability, and we produced a thrust level on the propulsion system comparable to drag. And the activities on the development of a breathing are ongoing with 2 different programs: an Horizon 2020 project that is focused on the development of the propulsion subsystem, and a national funded project that is focused on spacecraft architecture and enabling technology for such very low Earth orbit mission scenarios. And with this, I conclude the presentation, and I apologize for the long presentation.
Thank you very much, Tommaso. There's so much to say, so I think it's okay to maybe slightly overrun, but still we need to move on to our next speaker. The next speaker is Francesco Bautista. He got his PhD in aerospace engineering at the University of Pisa in 2009, and he currently works in CIRA since 2005. He's affiliated with the Propulsion and Exploration Division, and he is responsible for the Space Propulsion Office. He works as a system engineer and project manager in different national and international projects, mainly on the topics of methane-based liquid propulsion system, hybrid rocket propulsion, and electric propulsion. And today he's going to introduce to you the electric propulsion at CIRA, presenting the capabilities and perspectives. Francesco, the floor is yours.
Thank you very much for the introduction. Can you see my screen?
Yes, we can.
Okay. So I want to thank you for the invitation to this workshop. This is for me an important opportunity to focus on this argument related to the space propulsion and to present both CIRA capabilities and point of view. In the first part of the presentation, I will briefly talk about CIRA capabilities, and then in a glance I will focus on what we plan for the future. So electric propulsion is an important technology for space systems. This is mainly due to its indisputable advantages with respect to the other propulsion systems. This is confirmed also, as underlined before by my colleagues, by the increment of the spacecraft equipped with electric propulsion systems in last years. And this denotes a crescent interest of system integrators in this technology, inverting the trend of the early 2000s when there was only a moderate interest on this topic. So CIRA is constantly following the trend of the electric propulsion market and research that are mainly related to the mini-satellite market, and then, as underlined before, for next year to the future transportation systems, also for exploration purposes. The role of research is crucial because to overcome limits of the technologies is obviously important to invest in innovation and infrastructure for testing. So CIRA in 2015 launched a detailed electric propulsion plan to support the national and European industry working in this field with facilities and research competencies. This also to be able to cooperate as a research center and discuss in a field where different industrial players and universities have decades of experience and heritage. The program has been divided into 3 main lines. The first one is focused on the facility, medium-scale facility. The second one on the diagnostic systems, and the third one on experimental cluster design and numerical modeling. The program will end this year, and new investments, as we will see in next slides, will be done. One of the main outcome of this project is the electric propulsion laboratory. The core of the laboratory is the medium-scale vacuum chamber facility. This is a research and development facility for electric thruster up to 5 kilowatts. Its dimension is 2 meters of diameter, 4.5 meters of length. It has a pumping speed in xenon of 80,000 liters per second. And the attendance tests have been completed in January 2020. 20 and 21 has been dedicated to complete the laboratory area. and the hardware testing is foreseen by the end of this year. Some delay have been due to COVID pandemic, obviously, because the facility has been completed in a not lucky period. So these are the main subsystem of the MS2C facility. In particular, it is equipped with a multi-stage pumping system with cold heads. It has a dedicated flow controller for 2 cathodes and 2 anodes, and medium and high voltage pins for electrical connections. So it has pressure transducers for monitoring pressure in different sections of the chamber, a rotating rate equipped with Faraday and intrusive diagnostic in general, and different optical viewports, also with zinc selenide for application of optical diagnostics. You can also see that the internal walls are covered by graphite to minimize the sputtering. The performance of the facility has been verified during the acceptance tests, and the result confirmed that we match the requirements that we set at the start of the project. For what concerns the diagnostic, we acquired the split imaging camera, thermography camera, and we have a movable Langmuir probe rack with 3 Langmuir probe mounted on, and a Faraday probe rack, as I said before, that could be moved inside the chamber with a precision of 0.5 degrees. Now we are completing the investments, completing the manufacturing of the thrust stand with the company named Grado Zero, and some calibration activities are ongoing on the Faraday probes and Langmuir probes in cooperation with the National Institutes of Astrophysics. So then the test article line has been established in order to improve knowledge on design and analysis of electric propulsion devices. And in this line, we designed and built a 250-watt Hall thruster that will be tested by the end of the year. In the design of this thruster, we developed knowledge in different areas related to the electric propulsion devices design, as for example, thermostructural modeling and design, magnetic field modeling and optimization, and in particular, plasma modeling. The experience related to the design, the manufacturing, allows CIRA to better understand many issues related to the electric propulsion and to have an insight of testing and diagnostic needs. Moreover, in the smart work period in CIRA, we had the opportunity to improve on numerical models and tools, and we do a lot of upgrade, in particular on the hybrid plasma modeling code for electric thruster acceleration channel and plume modeling. You can see here the hardware we produced. Here there is our All-effect thruster, the cathode, and an electronic source that will be installed with the thruster for the first test in order to decouple two new hardwares. So, as I said in the introduction session, research is crucial for the development, and CIRA, thanks to the Ministry of University and Research, has started new projects to follow the need and the evolution of the electric propulsion and support the Italian system with investment and technologies and state-of-the-art facilities. 3 development lines have been identified that are in line with the trends in electric propulsion. The first one is to support low-power system development. The second one is to enable high-power thruster evolution, and the third one is dedicated to the incremental technology readiness level of innovative solutions in electric propulsion. So, going in detail, the first one project is more focused on the upgrade of the medium-scale vacuum chamber facility with the small vacuum chamber for subsystem development such cathodes, with liquid nitrogen in order to cool down the wall of the facility and to incubate all the area in a clean room. For what concerns the diagnostic, we are concentrating on the cavity ring down spectroscopy. We have a collaboration with the Circe Lab in Caserta, and then we are developing also a DLIF system with and then a neutral stand and new probes. For what concerns the design and the analysis, we want to advance our numerical code for plasma modeling, also adding new modules, and we want to demonstrate our design capabilities manufacturing a magnetic shielded low-power thruster. For what concerns high-power electric propulsion, the focus is the design and the realization of a big simulator for high-power thrusters, and all the subsystem in terms of diagnostic in particular to support the testing of this kind of thruster. We have a last line dedicated to innovative technologies because we are a research center. We want to make a trade-off on innovative concept at low technology readiness level and select two of them and demonstrate the scale up of the TRL manufacturing two of these concepts. A particular mention deserves the large-scale vacuum chamber facility. That is one of the main investments of the program. Here are reported the main features. From about 4 years, we are working on the idea of this facility. And we initially were skeptic because it's a big investment, but in last years, due to the particular development of the high power system, I showed before by Tommaso, also for exploration purposes, and to have an important asset for the Italian and European electric propulsion sector, we decided that this facility shall be made in Chile to support the current activity and long-term future plans on the electric propulsion. Is not a trivial path for a public institution like Chile, but we think that in about 5-6 years, the facility could be completed. So Chile has almost concluded its first stage of development in electric propulsion. And to conclude, I was just to underline that research and testing facility has a central role in electric propulsion system development for future mission. And so the public investment should be considered in this direction. Thank you for your attention.
Thank you very much, Francesco. So I think we are at the end of the first session. I hope you all enjoyed. I think there was a lot of information and a lot of interesting presentations. And with this, I give back to you, Marco.
And thank you very much, Katie, for sharing this interesting session. And thank you to all the speakers. It's time now to open session 2, that is electric propulsion in low Earth orbit and exploration missions. And I'm glad to have here from European Space Agency, Edward Bosch-Borras. He's a Master of Science in Aerospace Engineering. He received the degree in 2010 from Universitat Politecnica de Catalunya. And then at ISAE Superior in 2011, the master degree in space systems engineering. He is currently at European Space Agency electric propulsion engineer. Edward, the floor is yours. Thank you.
Thank you very much, Marco, for this kind of presentation. Welcome again to all the audience to this second block of presentations regarding the missions enabled by electric propulsion. I shall remind the audience that any question that you may have, you are invited to send them to the organization by email, and that this is not possible, let's say, to do it live due to technical reasons. Starting for our next, the first presenter, let's say, for the this block will be Camila Colombo, who is an associate professor at Politecnico di Milano since 2016, where she is the PI of several projects funded by ESA and an ERC starting grant on the Project Compass, which is the acronym for Control of Orbit Maneuvering through Perturbations for Application to Space Systems. She leads a team of 11 postdoc and PhD researchers working on the study of natural and artificial perturbations and their use for applications to space debris, modeling and mitigation, trajectory design, and mission analysis of missions involving constellations of satellites and formation flying and missions to near-Earth asteroids. Her presentation will tackle the EP-enabled mission in low Earth orbit, including large constellations and formation flying. Camila, the floor is yours.
Good morning, everybody. Let me share the screen. Can you confirm you can see properly the screen?
You can see the screen, Camila, but this is the presenter side.
Okay. Now you should see the correct one.
This is perfect.
Okay.
Thank you.
Thank you very much. Good morning, everybody. It's an honor for me to participate to this workshop. I will talk about some electric propulsion enabled mission in low Earth orbit, in particular focusing on large constellation and formation flying applications. So I will go through some of these applications, starting from the application of formation flying for distributed mission, for remote sensing or active debris removal mission, then application associated to large constellation, and finally some services enabled by low thrust propulsion like collision avoidance maneuver and orbit maintenance. Starting from formation flying is enable many different services because we are using a distributed set of satellite as sensors for creating a distributed node of sensor around the Earth. So the mission application of formation flying are several. And I will present the potentialities of using electric propulsion with one particular example. That is the example of a mission study that we are working on, funded by the European Space Agency in collaboration with Airbus Spain. That is a formation flying L-band aperture synthesis mission enabled by electric propulsion. The idea of this mission is to propose a new generation mission with respect to the SMOS mission. The SMOS mission was launched in 2009, is one single spacecraft mission and performs measurement in L-band. The current resolution of this mission that studies oceans and the salinities of oceans is around 40 kilometers. And we see here an example with an image taken from a volcano in Hawaii. The idea of the FFLAS mission instead is to have the same mission but perform by using a formation flying of 3 spacecraft with an hexagonal shape, still with measurement in L-band, and the estimated resolution is gonna go down to 1 to 10 kilometer side. How this is achieved? This is achieved by an L-band radiometer payload with a sun-synchronous orbit in altitude 775 kilometers. Is a triangular formation flying where very large satellites are needed to stay at a close distance of about 13 meters. So the control requirements are very strict and the control authority has to be very high. And this is enabled by the use of low thrust propulsion. Of course, these thruster performances are larger because the satellites are also larger. Is 4 thrusters in transversal and normal direction. So this is an example of a maneuver. This is a maneuver, a reconfiguration maneuver from Earth pointing to cold sky pointing. Here you see a video of the cold sky pointing mode. And in this image here, you see the configuration maneuver that each satellite has to perform, coupled with an attitude maneuver in order to move from Earth pointing to cold sky pointing. As I said, being a new generation of SMOS mission, the satellites are not nano spacecraft, they are of larger dimension. So the electric propulsion requirements are 4 ion thruster with a maximum thrust of 25 millinewton, delta V budget of around 1.5 kilometer per second, and propellant budget of around 100 kilogram. And this is the configuration of the 3 hexagonal spacecraft. Even this is a mission with larger satellite. There is also another mission concept that is studying interferometry from geostationary orbit, where the main satellite is a larger satellite, but the other distributed node are CubeSat. So also in that mission concept, low thrust propulsion is used on board of CubeSat to enable the frozen configuration, the formation of flying between the different CubeSat and the large mothership. So looking at formation flying application, what enable propulsion, what low thrust propulsion can enable is reconfiguration maneuvers, collision avoidance maneuver and orbit maintenance maneuver, deorbiting, and attitude control. Now moving to another very important and increasing application in low Earth orbit, I would like to focus on large constellation application. Why large constellation? Because there is a trend in increasing number of satellites in low Earth orbit to offer, for example, global coverage for internet connection and telecommunication, but also smaller size constellation like Galileo and GNSS for telecommunication purposes. The more the number of satellites increases, the more the constellation configuration becomes complicated. And due to the fact that constellations are commercial services, this is leading to the deployment of several constellations with different characteristics and stringent requirements. And in particular, a part of all the operation needed for guaranteeing the service of this large constellation, due to the fact that there are many satellites and there are many providers of large constellation, there is a need also to develop large constellation by harmonizing the deployment trend with space sustainability. So this requires responsible behavior by operator, for example, looking with some particular care the collision avoidance or orbit maintenance, orbit raising and the orbit, but also the need for new services. For example, new future services of removal services for failed satellite within constellation. So before jumping into the large constellation, let me just open a very short parenthesis in the complexity of performing optimization with low thrust, because of course, due to the fact that you have a continuum thrust, the optimization problem becomes a more complex problem to solve. One of the techniques that we use to do that is called the differential dynamic programming. That is a direct optimization technique, which can be summarized in 2 steps. A backward step, where we propagate backward the trajectory by guaranteeing optimality condition solved to find an optimal local control law. And then a forward sweep, where the new control law is used to check the cost reduction in the trajectory. And the optimality condition is translated into the Hamilton-Jacobi-Bellman equation. And this is an example of an application, for example, to a OneWeb-like satellite transfer, for transfer a OneWeb satellite-like from a release parking orbit of the launcher to the nominal orbit. And in here we can see the evolution of thrust and in the different direction and the constraint satisfaction. But let's go into the application of a large constellation. So first, as we said, large constellation need to be sustainable. So the orbiting strategies and orbit raising strategy performed with low thrust have to be designed with care, because we're not working with one single satellite, but with thousands of satellites. In this work, we have compared two possible deorbiting strategy. One that is only with low thrust, so a low thrust maneuver at the end of life, used to lower the perigee altitude of the satellite until the drag-dominated region, where the drag effect will be strong enough to lower the apogee altitude until re-entry. But one maybe a bit more futuristic application of low thrust propulsion is that it will couple with natural orbit perturbation, or with some novel ways of propulsion that exploit the effect of orbit perturbation. And in this example, I show you the coupling with low thrust propulsion with a solar sail or a deployable balloon, in a way that low thrust propulsion can be used to move the satellite, not really until the re-entry condition within the atmosphere, but maybe in an higher orbit where, however, the effect of solar radiation pressure is high, and then at that point to deploy and artificially increase the area to mass ratio of the satellite by deploying a balloon or a solar sail. Of course, the design of this second strategy, the configuration design of the satellite, is going to be more complicated, because we are going to have in orbit, on board, not only the low thrust propulsion, but also a deployable balloon. But this strategy could be used to reduce the operational time, because we could leave this second phase to be a passive deorbiting phase. And here we see the trade-off between these two strategies. So the orbiting only with the low thrust propulsion, or the orbiting with low thrust propulsion, so an electrical engine plus a deployable balloon. In terms of initial altitude of the constellation and initial orbit inclination of the configuration. In the blue area, we see that the delta V budget of a low thrust only strategy is lower than electric propulsion plus solar radiation pressure strategy. So strategy 1 is better, but there are some initial conditions in terms of initial inclination and initial altitude, where actually the effect of natural perturbation could be exploited, and therefore the total delta V budget, considering also the mass of the satellite with low thrust propulsion plus solar sail, would be better. Another application associated to large constellation and low thrust propulsion is orbit raising and deorbiting, considering the additional constraint of self-induced collision, because the collision might happen between satellites from the same constellation when one of them fails, because they pass at very low distances between each other. So in general, the goal is to reduce the collision risk when multiple satellites perform orbital transfer at the same time. So when we are performing orbit raising or deorbiting. In this application, the control law design is a self-adaptive design for an onboard guidance, due to the fact that we are having a huge number of satellites, of the order of 1,000 of satellites. And how can we achieve self-induced collision avoidance? By designing the control law to maximize the instantaneous relative distance between the satellites of the same constellation, and optimizing the timing to start the orbital transfer of every satellite, that therefore is not treated anymore as a single satellite, but as a series of satellites that are coordinating together for performing the orbit raising or the deorbiting. Another application still associated to this is the deployment, because when we perform the deployment of a large constellation, we want to do that very rapidly, because we are providing a commercial service. So the shorter the satellite takes to reach the orbit, the better it is for the revenue of the service provider, by using high performance low thrust technology. So the deployment consists in the distribution of multiple satellites from the same parking orbit, because usually they are launched with a shared launch, into different desired orbital plane and orbital configuration. The goal is to do that rapidly with the aid of high performance low thrust propulsion and by minimizing fuel consumption. The methodology is again in some way to exploit the very good coupling between low thrust propulsion and natural perturbation, because what we can do is to have three phases where we use low thrust propulsion together with the exploitation of the J2 effect, the Earth oblateness effect. So there is a first phase of pausing at the parking orbit to wait for the raising of the orbit at a predetermined time interval where no control law is applied. Then the second phase is the raising to the operational altitude, where we have in-plane tangential thrust, and then a third phase of an out-of-plane phasing maneuver for predetermined time interval until the desired right ascension of the ascending node separation is achieved. And in these three different phases, the effect of J2 is exploited to actually achieve a delta run variation for free. In this slide, I reported some example in terms of the deployment cost trade-off, in terms of the time, so the time for each satellite and the fuel consumption of each satellite. And the shaded area represent the fuel consumption space for a satellite, for a transfer between two OneWeb-like satellite to be deployed into two different orbital plane. And in here are the characteristics of the low thrust engine used for this particular simulation. So, then the additional service that will be needed due to the fact that we have a large constellation is removal services, because satellite within large constellation will fail and therefore will look for a service of active debris removal. And I take an example, I take as an example a project that we have been working on with the European Space Agency and the orbit of the design of an active removal service for large constellation, considering two constellation case, a light scenario, so 150 kilogram spacecraft, and an heavy scenario, so 750 kilogram spacecraft, like a Telesat Constellation-like. Three architecture of mission were considered: a mothership plus a kit, where the mothership that could be equipped with low thrust propulsion carries spacecraft kits to perform the removal service, the chaser, and where the unique chaser perform the service, and a chaser plus station, where a station is used to refueling the chaser once the propulsion is the propellant is over. The design driver are the delta V cost, the launch system constraints, and the business case for the removal service. For one of the two examples, so a OneWeb-like constellation example, the so-called light case scenario, we analyzed these three possible architecture of mission, and we perform a trade-off in between the number of satellites that can fail within the constellation and the preferred architecture given that number of satellites. In particular, we can see that the mothership plus kit architecture is a good choice for a high failure rate scenario, for example, 9 targets in 1 or 2 adjacent plane. The Chaser plus station option is the good option for many failure in many planes, while the premium selected option for a few number of failure, no matter where the failure is in terms of orbital plane and orbital position within the plane, is the Chaser architecture. For all this architecture, I want to stress the fact that, again, we are exploiting the use of delta V maneuvers plus the effect of orbit perturbation. And in some of this architecture, the use of low thrust propulsion could be beneficial for increasing the life operation of such a service, and therefore improving the business case for this service. And so to summarize, what are the...
Sorry, Camila, I hope that this is the last slide.
Yep.
Please running late.
Yes.
Thank you.
So to summarize, application for large constellation in LEO are the orbiting, also enhancing the effect of orbit perturbation, orbit raising, again, exploiting low thrust and orbit perturbation by avoiding self-induced collision, on-orbit maintenance, and active debris removal services for large constellation. With this, I stop with my presentation, and I thank you for your attention.
Thank you very much, Camila, and sorry for the interruption. As mentioned, we're running late, so unless there is a very short question from the speakers, we will continue to the next presentation. Activities involved in spacecraft flight dynamics, interplanetary cube submission, and system design, autonomous guidance, navigation, and control. Professor Toputo is an ERC laureate and leads the Deep Space Astrodynamic Research and Technology Group, also mentioned as DART. So the presentation about interplanetary missions to the moon will be presented by Francesco. The floor is yours.
Okay, thank you, Edward, and good morning, everybody. I'm glad to be part of this very interesting workshop, and therefore, thank you for inviting me to the workshop. I'm sharing the slide. Let me see if everything works. Okay, can you please confirm that you see the slides in full screen?
The slides are there and not in full screen. Now it is.
All right, thank you. And again, my name is Francesco Toputo, and I will try to give an overview of the importance of electric propulsion for miniaturized missions with applications to small body and lunar missions. And in doing so, I will use the experience we have accumulated here at the DART lab at Polimi in a number of different projects we are involved together with the European Space Agency, and as was mentioned a minute ago, in the ERC-funded project called Extrema. So as it can be seen from this slide, we are involved in three missions, and I would like to spend a couple of minutes in the high-level research that we conduct here at the DART lab in order to understand the importance and how electric propulsion can enable novel mission concepts in order to answer the key question of today's workshop. So, as we all know, there is a current trend going on since a couple of decades already in order to miniaturize the probes to reduce the costs and in order to make the space accessible to small entities. However, for what concerns deep space exploration, we still have monolithic spacecraft in which we have very good performance, but a lot of control authority, for instance, but also this comes at a cost. The idea in our community is to go for miniaturized components in order to, by following the miniaturization of the electronics, but however, when it comes deep space exploration, it's a little bit tricky because it's not like using CubeSats in low Earth orbit, but there are a number of challenges that have to be solved, namely generating power, propellant, propulsion, exerting enough delta V, for instance, communication, and so on and so forth. Therefore, there is the concept of interplanetary CubeSats that is nowadays quite common, and the CubeSat missions for deep space exploration can be divided into two main branches. One is the family of missions belonging to those that are released in situ upon arrival, and they are usually passenger of a bigger mission. For instance, let's think of the CubeSats aboard Hera, which will visit the Didymos double asteroid system in 2027. Or let's say the more interesting one are those which are standalone. So deep space CubeSats that perform a standalone cruise in deep space. Well, I have the latter, so the CubeSat that perform a standalone cruise in the deep space are, I would say, the most important one for today's workshop, because we're talking about primary propulsion, we're talking about electric propulsion, and those missions, they require some significant delta V in order to perform heliocentric orbit transfer. Now, I would use the experience we have accumulated in the framework of the Miniaturized Asteroid Remote Geophysical Observer, also known as MARGO, which is a NISA mission study for standalone CubeSat, whose phase A was concluded last summer, and phase B is hopefully going to start very soon, in order to highlight the importance of enabling miniaturized electric propulsion for this kind of mission. Let's see what we can do if this technology that currently does not exist, or maybe the currently available solutions are a little bit borderline in order to be applied for this kind of machines. So as I was saying, how this solution can be an enabler for totally new space missions, exploration missions. Now, an overview of the concept that was studied. The credits go to the European Space Agency, and namely to the Interplanetary CubeSat office, and to the Concurrent Design Facility that back in 2017 they put together a CDF study, which was also translated in the form of a phase 0 study for a 12U CubeSat, as I said, named MARGO, whose aim was to rendezvous with a near Earth object and to characterize this object as a precursor of a bigger space mission in the framework of in situ resource utilization. So the concept looks like the CubeSat with the two deployable solar arrays, and there are a number of technological demonstrations. For instance, the X-band transponder, miniaturized one, which currently doesn't exist in Europe, and it's being developed by a company here in Italy under ESA contract. The reflect array, deployable reflect array, which is being developed in Denmark, if I'm not wrong. And last but not the least, the miniaturized electric propulsion, which, as I said, has been assumed, whose performances have been assumed, but the hardware component does not exist yet. Now, the assumptions that we took were to have a mission time frame lasting 2 years. This was back in 2019, so I would say that the departure window doesn't apply anymore, but it needs to be shifted. But most importantly, we have the transfer time lasting 3 years, and up to 6 months of the close proximity operation around a minor body. The idea was to have the CubeSat parked at Sun Earth L2 and released there by being the passenger of a bigger Lagrange point mission. And the figures to remember are the propellant mass, 2.8 kilogram, compared to spacecraft wet mass, which here is written 22.6, but we can assume it's around 24 kilograms now. And as I said, it's very important to highlight that the departure point is Sun Earth L2, not therefore low Earth orbit. So these were the electric propulsion performance assumptions that we took. This was an educated guess that was discussed with ESA and with the company that was at that time supposed to develop the miniaturized ion propulsion thruster. The idea is to have at 1 AU an input power of around 100 watts, and at this distance from the sun, with this power, the thruster has to be able to exert 1.9 millinewton of maximum thrust with around 3,000 seconds of ISP, as you can see in the figure on the bottom right. And on the right y-axis, you have the ISP. On the left y-axis, you have the thrust. Of course, the performances change by changing the input power, which in turn is a function of the distance from the sun. Therefore, the what we call realistic thruster model, which was this one, had to be included in the exercise aimed at assessing the number and targets that could have been potentially accessible from MARGO. So the idea was that we had these assumptions, and we didn't know how many asteroids could have been assessed by this system. Therefore, we, of course, this is a very long story short, so we ran a number of, developed a number of tools by scanning the minor body planet database. And at the end of the day, by solving what we call time optimal transfers, we found out that a number of asteroids were reachable. And by imposing the propellant mass threshold, which was slightly higher than 2.8 here, because we were confident that in the fuel optimal step, this propellant could have been reduced, and by imposing the 900 days of time of flight, we found out that 125 asteroids were potentially reachable. Now, this is a very important figure because in the previous studies carried in-house by the European Space Agency, if I'm not mistaken, it came out that only a few tens of asteroids were reachable. This was for time optimal. Then we ran another step in which we solved for fuel optimal transfers, and for each target we were able to produce this, let's say, pork chop-like plot, in which on the x-axis you have the departure epoch in modified Julian date, and on the y-axis you have the transfer time. The red line on the bottom part of the plot is the time optimal solution. You cannot go below that line, so the dashed region is what we call the forbidden region. And for each point of this plot, you have a different transfer. And for instance, you have a classic time optimal transfer in which the thrust is always on. The thrust is in these subplots, the one on the top right part of the subplot. When you increase the transfer time, you can see that the amount of thrust required decreases, and so on and so forth when you go all the way to 900 days. So this is to say that with these exercises, we produced a number of pork chop plots, and later on we pruned together with the prime contractor, the European Space Agency, and some experts of minor bodies, we compiled a list of the shortlisted targets. At the end of the day, they were fully reachable with quite wide departure window and reasonable transfer time, around 42 asteroids. All the process, all the results, and the details of what I just shown can be found in the paper that is pointed in the bottom part of the slides, for which I acknowledge the enormous work of the co-authors there. But the takeaway message here is the following, that we can enable this kind of missions. These are new missions. There is no analog for current missions of the deep space CubeSat traveling alone in the deep space. So these missions can be enabled if we are able to guarantee electric propulsion thruster that are able to perform as in the assumptions that I shown in one of the previous slides. So produce around 2 millinewton of thrust with around 100 watts of input power, build up a total delta V of around 3 kilometers per second, operate for hundreds of days, and be compatible in terms of mass and volume with the CubeSat requirement and form factor. If we shortly see what happens in the lunar environment, I can bring and share the experience that we have accumulated with Lumio mission, which is another CubeSat mission that is supposed to orbit Earth-Moon L2 in a quasi-halo orbit. This is for the purpose of monitoring the lunar far side in order to detect impact flashes that are produced whenever a meteoroid impacts with the lunar surface. Now, the idea, I'm sorry if I go back, but if we look at the mission concept, the cartoon there on the bottom left part of the slide, we can see that the assumption here, this is already again agreed with the European Space Agency, and the phase A of Lumio was over earlier in the spring of this year. The assumption is that the CubeSat is released in low lunar orbit, and once there, it will perform an autonomous transfer. Autonomous means by using its own propulsion means, okay, from the low lunar orbit all the way to the Lagrange point orbit. It's a transfer that overall the mission might require around 200 meters per second this time. So the orbit was a halo orbit that had a number of pros. It was selected because it's a very good orbit in order because it's eclipse free, for instance, and because you can always see both the moon and the Earth while there. So in order to assess this orbit, we studied chemical propulsion. In this case, it was considered the cold case propulsion in order to cold gas propulsion in order to go from low lunar orbit to the yellow orbit, and the transfer cost was around 80-90 meters per second, and we found a number of different options. Another option, instead of being released in low lunar orbit, was to use Artemis 2. Artemis 2 is able to release CubeSat in some sort of bus stops, in which the CubeSat is injected into a lunar encounter orbit, and once from there, one has to apply a number of maneuvers to acquire either Sun-Earth L2 or intercept the moon by leveraging, in this case, the simultaneous gravitational attractions acting on the CubeSat and exerted by the Earth, the Moon, and the Sun at the same time. At the end of the day, this was to say that in studying the phase A, we had considered to use low thrust propulsion from low lunar orbit to reach Earth Moon L2. But this was discarded because of essentially high transfer times and difficult operations in this case, and therefore the cold gas propulsion was baseline. But the takeaway message for miniaturized missions in cislunar environment is that electric propulsion can enable this kind of missions if we are able to produce more or less the same thrust with the same input power as in the previous case, an order of magnitude less delta V in the order of 200 meters per second, operate for a few hundreds of days. The nominal lifetime of Lumio is 1 year. And as before, everything has to be compatible with the volume and mass constraint of a CubeSat, because Lumio is, again, a 12 units CubeSat, as it is the case of M-Argo. Now, again, I've pointed out a reference down there just for the details on the process of how the operative orbit of Lumio was selected. And with this, it was just a short overview in order to bring my experience with these two missions and to share, let's say, the needs for miniaturized electric propulsion in order to enable novel mission concepts at both minor bodies and cislunar environment. And yeah, that's it for my overview.
Thank you very much, Francesco. Is there any question among the rest of the speakers to Francesco? No? Okay. Otherwise, then we'll thank again to Francesco for this nice presentation.
Sure.
And
I'll be back for the round table. So, yeah.
Thank you. There sure will be time to discuss in more detail the missions that you just presented and the requirements and the complex technical technologies that need to be developed to make these missions a success.
Okay, thank you.
Thanks very much. Our next presenter will be Ms. Sabrina Corpino, who is a PhD and Associate Professor of Aerospace Systems at the Department of Mechanical Engineering and Aerospace Engineering of Politecnico di Torino. She qualified for the position of full professor in 2020. She is the Director of the Systems and Technologies for the Aerospace Research Laboratory, StarLab, and she leads the CubeSat program of Politecnico di Torino. She has extensive experience in the field of space systems, design and development, with focus on design methodologies for complex systems, including optimization techniques, stakeholder needs analysis, and design trade space exploration methods, and development of small space platforms and end-to-end missions. She will introduce the ESA CubeSat test bench for electric propulsion systems, which I'm happy, let's say, to collaborate, let's say, from the ESA point of view. And in case, let's say, there is any question from the speakers, I will also be happy to participate in answering them. So, Sabrina, the floor is yours.
Can you see the screen?
Yes, we can see it.
Okay, thank you very much, Edward, for your kind introduction. And thanks for inviting me to this unique forum to discuss about a very hot topic in space engineering. Good morning, of course, to all the audience. And we have seen and listened to very interesting and fascinating presentations so far. Now I'm going to change a little bit the perspective, as we are going to talk, as Edward already mentioned, about a different kind of project that is about a simple test bench for testing electric propulsion systems. The project, as anticipated, is a collaboration between the European Space Agency and Politecnico di Torino, and it was initiated on the basis of some considerations. The first, look at this picture. We see here the part of the ESA's CubeSat fleet, which is not exhaustive of all CubeSats developed at ESA or in collaboration with ESA or supported by ESA. But this picture gives an overview of what's happening in the CubeSat mission field. So many of these missions have been completed. Some of them are ongoing and others are on their development path. We see here a mission in low Earth orbit, other hidden farther destinations such as the moon and asteroids, as Camila and Francesco already described for the mission in which they are involved. It must be said that very few CubeSats in this picture have propulsion, whatever propulsion on board, but many of these really need propulsion. Another interesting picture to share and to comment together is the forecast of for nano and micro satellites, let's say below 50 kilograms, in the coming years. We expect to have more than 2,000 launches in the next 5 years. Someone said something like 3,000 launches. So the result is that space is getting more and more crowded. And I think that propulsion will be key to this for this market development. Looking at the potential roles and applications of small satellites, I refer in particular to those showbox-sized satellites in the coming years, or maybe in the coming days. I would say that they will still keep their value as a training opportunity for future generations of space professionals, of course. But something new is happening. Okay, why is not changing the slide? Sorry, guys. Cannot change. Okay. But more interesting missions are coming. We are entering a new era, as we are all aware, with the more challenging applications and goals to be pushed. In this case, the pictures refers to studies that have been done with ESA, at Politecnico di Torino, with ESA, and with the support of ASI for the inspection of the International Space Station, or maybe in the future lunar stations, and also for debris inspection, or also for this is a special mission as ROC for the inspection of Space Rider. These kind of missions involving proximity operation will require very demanding requirements in terms of propulsion capabilities. But going further, there are new destinations on the horizon, as Francesco mentioned before. This is a nice picture taken by Marco in 2018 in his way to Mars. So there are also other applications that are extremely interesting. I don't know why. Okay, sorry for that. There are also other very interesting applications as for providing services in the domain of Earth observation. As you can see on the left-hand side, this is a nice picture taken by a 3U CubeSat of San Francisco. But also other application in the domain of Internet of Things. We are all aware of OneWeb, SpaceX, mega-constellations, and so on. So all these new missions will require new technologies in several domains to pursue the very ambitious goals with these tiny satellites, improving, of course, safety and reliability on one side, but trying to keep the successful paradigm that we call low-cost fast delivery. In my since 2016, it's no more operative, but almost alive. And periodically receives carrying messages from the space track organization, as you can see here, followed by the crash support at ZOC, asking me what can I do for, sorry for the noise on the background. What can I do? How can I try to avoid the collision? My answer is always the same. That is, sorry guys, I have no propulsion on board. Okay, and the only things I can do is to cross my fingers, actually, like this little girl. And every time I receive one message like this, I promise to myself to put an electric propulsion system or a propulsion systems in general on board my next satellite. However, that being said, and not to go too long, we identified, talking with ESA and with many stakeholders, that electric propulsion could provide many a big support to solve many of the issues that we are facing as integrators and systems engineers. At different level, from design and development to verification and demonstration. And in particular, that's why we decided with ESA to start a project that we call MicroProp. And the main goal of this project is to offer a one-stop test facility at a stack for CubeSat with propulsion system, including tests needed for supporting the qualification of the CubeSat for the launch at system level, not only of the thruster, not only of the platform, but all of the flight unit as a whole. So to perform functional and performance tests and to perform environmental tests, I mean thermal vacuum, mechanical, and so on. We can draw two objectives from this main goal. The first is the need for the assessment of the effects of the operations, I mean the interactions between the miniaturized propulsion systems and the CubeSat platforms in terms of, for example, electromagnetic interference or the thermal behavior of the whole platform, the electrical power consumption and contamination, and so on. The second objective is to develop tools and procedures for testing propulsion systems at system level in terms of test requirements, measurement requirements, the definition of standard test plans and procedures, and of a qualification process that exists for traditional, let's say, satellites, but there is a gap instead in the small satellite and in particular in the CubeSat world. So the project developed through several phases, starting in at the beginning of 2018 with a feasibility project to demonstrate the possibility to build a test platform for hosting electric propulsion system, and the result was a prototype, something like an engineering model of a platform to host propulsion systems. The second phase instead had the objective to assess the mutual effects of an electric propulsion system and the CubeSat test platform, with the integration of the first propulsion system in our platform. And it's a pleasure, Daniele is here to say that this propulsion system was the Regulus propulsion system by T4I. We completed the first test campaign in very difficult conditions during the pandemic. But the test was successful, and we learned a lot. We learned a lot during the test campaign. We, of course, as always, and especially during let's say the first test campaign, we discovered a few bugs and so on, but we fixed all the problems during the campaign, so that the campaign itself could be completed successfully. And now we are in the third phase. The third phase aims at, let's say, supporting not only electric propulsion system developed, but also CubeSat primes. Because what we want to do with this project is to perform a complete qualification campaign of an all-electric CubeSat, including also a mission simulator that can drive the platform during the test. I have some slides summarizing the characteristics of the platform. That of course we can go into the details if you have questions and so on. But just few comments on that. The first two platforms were the form factor was the 6U. With up to 4U available for the propulsion system to be tested. We could provide about 50 watts for the propulsion system at different voltages. We implemented several data interfaces and other things that you can read here. The platform, of course, is equipped with many sensors for measuring different parameters related to the operations of the propulsion system, and also of the avionics of the platform itself. These are nice pictures of the environmental test conducted at Padua with the T4I. You see here the thruster, and also here.
Sorry, Sabrina, to interrupt you, but we're getting late. Please, I know that the presentation can get very long and there is a lot of details to explain, but if you can concentrate.
No, of course, I'm not going into the details, but just to share the last version of the platform, that is a 12U. So the size is increased. And we decided to increase the size to provide more opportunities to the electric propulsion developers that are interested in more in bigger satellites, let's say. We of course improve some features of the previous platform. For example, we added more data interfaces. We increase the power that can be generated for the electric propulsion system, and so we will more than glad to hear from the electric propulsion system developers about their interest in testing with this platform their developments, their products. And with this, I have concluded. and thank you very much for your attention.
Thanks to you, Sabrina, for this nice presentation. Maybe just to add, for anybody that would like to have more information on this platform, there was one of the references that you mentioned here that was presented in the last Space Propulsion Conference, and anybody probably can find the article online. As you mentioned, that we plan to have the commissioning of this third iteration of the platform before the end of the year. So hopefully we will be able to present the results by the Space Propulsion Conference next year. Hopefully.
Thanks.
So thanks, Sabrina. I don't know if there is any short question from the speakers. No, then thanks again. And then we will close this presentation. And with this presentation, we close this second block of presentations. And then we move to the roundtable, which will be chaired by Marco Di Clemente.
Thank you, Edward, very much for chairing this session about the missions enabled by electric propulsion. It's time for the last block that will be slightly more than half an hour. I welcome Marco Di Clemente from the Italian Space Agency. Marco is PhD in Theoretical and Applied Mechanics and is with the Italian Space Agency since 2017. He is the head of the technology unit in the program directorate, with the main duties to ensure the technological coordination within Italian Space Agency activities and to define, coordinate roadmaps in the implementation of the coordinated roadmaps. He is member of the Italian delegation at ESA Industrial Policy Committee, and he is the national Italian delegate at the Technological Harmonization Advisory Board and member of the Space Component Steering Board and advisor of technical assistance for ECSS. A lot of roles for Marco that are in some way connected to what he is going to present today, that is an harmonized view to foster the benefits of the electric propulsion. Marco, please, the floor is yours.
Thanks a lot, Marco. Thanks for the presentation and for inviting me to this event. So yes, as I said, this is the last session of the event. There will be this roundtable. So before starting, I would like to introduce once again our speaker for the talk. We will have Sabrina Corpino that just presented her activities. Sabrina, as said, is associate professor at Politecnico di Torino. There will be Francesco Bautista, responsible of Space Propulsion Office at the Italian Aerospace Research Center. Daniele Pavarin, founder and CEO of T4I, Technology for Innovation. Francesco Toputo, full professor at Politecnico di Milano. And last but not the least, absolutely, Tommaso Misuri, who is the head of propulsion department at CTEL. So I would like to ask the speaker in case to switch on the camera and of course so we can see each other. Thanks for being here for this discussion. As you see, we have a representative from industry, from the academia, from research center. So I'm sure that the discussion will be really fruitful today. So in order to set up the scene, I have a couple of let's say remark that maybe could help even for future discussion for the talk. As we see, the electric propulsion is considered probably really a key enabling technology for future missions, and there is a lot of interest on the commercial side, but also for scientific and institutional missions. And there is a lot of effort already done, almost by let's say, all the space agencies in Europe, outside Europe, by ESA, by the Commission. So I would like to ask to the speaker today, in your opinion, according to your feeling of the knowledge of this technology, what are the needs to be addressed in order really to have to enable space mission based on electric propulsion? Which are the technology developments that shall be achieved, or maybe shall we need to increase capabilities for design, for testing, whatever. So please, I would like to ask first from let's say the academia point of view. So Francesco and Sabrina, feel free to say and to give us your overview on this.
Okay, maybe if Sabrina allows, I would just say my very short point of view, and then I will leave the floor to her. As I said, there is a piece of technology currently missing in Europe, which is miniaturized ion propulsion, which means thrusters being able to produce 1 to 2 millinewton of thrust with 300,000 ISP at 1 AU, more or less. So for what I presented and for what I saw during the recent years, and also for my experience in the 2 missions that I presented, there is a gap. There is a gap in Europe that needs to be filled by this kind of technology. Now, I have to apologize if I'm not aware of any other substitute, because I'm not a propulsion guy. But at least this is my point of view. So there is this gap. I'm not sure how much difficult it is to scale down ion propulsion. I know that, for instance, CITAL has a number of solutions for miniaturized Hall effect thrusters. But as I said, the ion propulsion is not an option that is out there yet. This is my point of view.
Okay, Sabrina, do you want to add something to this?
Yeah, also, as Francesco, I'm not a propulsion guy. But what I've seen recently, we have made a survey, and we contributed to the development of the harmonization dossier for miniaturized propulsion. And what we have noticed is that there are many developments in Europe regarding electric propulsion. If I'm not wrong, about 45 developments, but very few of these developments are at high TRL. So I think that it is worth to push a little bit, maybe on the most promising of them, to achieve a TRL, let's say at least 6, in order to have more insight in the validity of the technology. Because we have seen there are many ideas, in some cases super exotic ideas. So I think that we need, especially from the space agencies, I think, an harmonization action in order to try to achieve the right level of technology that we need for implementing the missions that were presented by Camila and Francesco, and other missions that are ongoing, of course, because we have really many ideas, many developments from very small companies and so on. But we don't really have insight in these technologies, and maybe it's worth to to try to push some of them, at least, if not all, to a higher level of readiness for demonstration, first on ground and then in orbit. And also the possibility to have in-orbit demonstration. This is also extremely important.
Yeah, thanks, Sabrina. You show us a very interesting presentation regarding the testing facilities available now at STEC. So maybe what you said, the idea to push for in-flight demonstration, even to correlate probably the results on ground now with the what we can be achieved now on in-flight conditions. And in this perspective, maybe Daniele can add also some. He has actually a flying propulsion systems, not yet operated, as we heard before. What do you expect from this, Daniele? First, from this demonstration, and then regarding the needs that have been addressed by Francesco and Sabrina. Can you, let's say, accept this challenge, T4I or CEDAR, of course, or other players?
Yes, thanks, Marco. Well, I think that support from the agency is very important. As Sabrina was mentioning, there are different technologies that can play a different role on the theater of propulsion solutions. So many different needs, different solutions. So there are multiple offers. But at the end of the story, the problem is to take solution to a TRL, to a very high TRL. So what Sabrina evidenced, I think it's highlighted, I think it's important. And one thing ESA is doing is to make available facilities, and I think it's a very important step. But the second point is in-orbit demonstration. And for electric propulsion specifically, I think that in-orbit demonstration provide challenges that are difficult to face for a single company. So I would really like if agency could help companies in addressing this issue. So differently from our system, when you test an electric propulsion system, you require a certain amount of power, which normally is higher than our subsystems, and that's the first challenge. The second challenge, you need continuous operation for a long time, which means that sometimes the satellite cannot do anything else for months. And this is also a problem. For example, when we had to undergo in-orbit demonstration, we selected the different operators. But we find ourselves on one side to have high cost, and on the other side to have limited power and limited type for operation. So basically, for example, one operator told to us, okay, but you should be happy, we will turn you on for 10 days. And we say, okay, but 10 days is nothing for an electric propulsion system. And just to see that probably, I will see that the thrust is fine if I'm lucky, and it's not even easy because it depends on what you do. If you have to make an orbit change to measure thrust, it's not even enough, and that's it. So it's not really enough. The third point is to have availability of missions. So to have a lot of missions, a frequent mission to validate the system in orbit to be very helpful. So I believe that agencies could help a lot propulsion system developer with this.
So with the mission specifically devoted to in-orbit demonstration.
Frequent missions. Frequent missions, so don't have to wait for years to have to complete. For example, there was a call from the European community to give a free option to fly on a system launched by Vega. We've been selected, but it's now I know that it's back to its path. But it was I think 1.5 years ago or 2 years, so it's really a long time. Companies require to have flight opportunity. Ideally every month, of course it's impossible, but let's say every 6 months, it would be very good. And then to have satellites suitable to do what is needed for an electric propulsion system. So providing enough power and enough operational time. Everything at a cost compatible with the budget of a small company, which of course cannot be zero, but need to be, if agencies want to push for innovation, that's something that they need to find out to cope with, I believe.
Yeah, for sure. Especially we are addressing in this first part of the talk mostly, as I understood, propulsion for CubeSat, so small, very low power, small propulsion systems, and maybe in this case probably the time that institutions or agencies, even ASIAN and Euro and ESA, shall be, let's say, coordinated with the short time to market needed by the companies, as you, Daniele, addressed. And on this, speaking of other dimensions, let's say higher dimension, I would like to involve or Francesco, Cira, or Tommaso to give us the needs on the opposite side, let's say on propulsion, on electric propulsion for let's say traditional satellites that could be enabled by this kind of technology.
Yes, I can say that to obtain high specific impulse, electric propulsion system needs a high power thrust ratio. And so we need power systems capable to generate several kilowatts. So it's important to invest in efficient power generation system and power processing unit. And also, I think that is very interesting to invest in the direct drive technology option. And I find very interesting the presentation from CIREL, where they equipped the facility with a direct drive simulator. And I think that such an investment could be important for us in order to upgrade our facilities in Cira at service for the industry.
Okay, thanks a lot, Francesco, for this for addressing this. Of course, as addressed, the propulsion system, the electric propulsion, is addressed other subsystems of the of a satellite, starting from power generation. That is probably the main constraint. We are dealing nowadays with mostly solar power generation. Maybe in the future there could be other technologies, but before opening a new door, maybe too much for today. Tommaso, which is your feeling about this?
Yes, actually, I was going to open. Yes, I was going to touch this point as well. I mean, thank you for the question, because we have internally this distinction between low power electric propulsion and high power electric propulsion, which is not entirely fictitious. Of course, it's bound to our history. We have developed a certain number of thrusters. Some of them are intended for small spacecraft. Some others, like the 20 kilowatt thruster, of course, is something that we would like to use on large spacecrafts for space exploration. So there is a distinction also on the key performance aspects that we keep under control and that we evaluate more for one kind of propulsion and the other kind of propulsion systems. So for low power thrusters, like the one that we are basically using as baseline for the future Platinum mission, HT100, there we are focused more on aspects linked to the cost, the production of the propulsion system, the entire propulsion system. So the focus is more on rate of production, reducing costs. About one point that has been touched before, the possibility of scaling these thrusters down, because of course we have talked today quite long about very small satellites. CubeSat, 3 units, 6 units. Okay, whole effect thruster technology, like also gridded ion engine, is quite hard to be scaled down to a certain level, because then you have a power to thrust level that becomes increasingly worse. So when you are going down with the size, in the end, you will need proportionally more power to generate a certain thrust. And it could be quite challenging to have in a single unit a system that has a specific impulse of 3000, as Marco was suggesting before. And of course, this would be desirable. And the thrust of 2 millinewton. So there are devices, different devices, usually FIP thrusters, for example, that can provide a very high specific impulse, but a lower thrust. We are in the range of micronewtons. While on the other side, going back to your question, high power thrusters, so even up to 20 kilowatts, one of the most important challenges is to test these thrusters on ground, because of course it's not possible to have an in-orbit demonstration. Okay, at the moment it's not possible to have an in-orbit demonstration even of a 5 kilowatt thruster. It's quite challenging because you have to put it on a large spacecraft. So you need to have good facilities on ground, and it's not so simple, because when you are dealing with a 20 kilowatt thruster, you have a very large mass flow rate, and to keep the background pressure very low during the test campaign, you need large chambers and very high pumping capabilities. So this is a problem. And then on orbit, the other problem is, of course, to make sure that we have a power generation system, and not only a power generation, also power distribution system that is able to generate and handle tens or even hundreds of kilowatts. So the nuclear thing that you were mentioning, of course, is absolutely interesting if we have to go tomorrow in exploring space with very high power electric propulsion. I don't know if it has been mentioned in the presentations, but of course it's top.
Okay. Yeah, thanks a lot. And Francesco Topudo, please, I see you and your raise. Yeah.
No, I just wanted to throw a stone there in the lake, but I mean, as I said, the foreground is that I'm not expert, but because we have some tools to study new mission concepts for what concerns astrodynamics and low thrust trajectory design. I wanted to share with you an idea for which I had been contacted a few months ago by colleagues from abroad. Of course, I'm not sharing many other details, but there was a very futuristic call for deep space exploration, and the idea was to try to see where we can be in 2 decades from now. So if we think of 20 years from now, so they asked me if I was able to assess completely new missions in the solar system, if I get a thruster able to produce 100 kilometer per second of delta V. As I said, this is very far in the future, but now, of course, this is not a reachable level nowadays. But as I said, I wanted to throw the stone for a discussion and for the companies and for the experts. How far we are from this level, I would say very far. But do you think we can reach this level of having missions able to produce 100 kilometers per second of total delta V in 2 or 3 decades from now? This is not for tomorrow, but it's for
a long-term, let's say,
yeah,
development. Tommaso, we will have this kind of performance?
I'm thinking out loud, of course. I wasn't prepared for this question, but it's super interesting. if we have to reach such a high delta V, of course, in the end, if we don't have a very high specific impulse, we will end up with having basically all the mass of the spacecraft being propelled. So 100 kilometers per second is very tough. I'm not sure that with the present technologies, so with specific impulses that range between 2,000 and 3,000 seconds for electric propulsion systems, this can be easily attainable. Of course, there are advanced systems that promise a higher exhaust velocity, but at the moment, the technology readiness level is very low. There are more concepts that are being explored than real thrusters. If you have to build up 100 kilometers per second with our, I don't know, 20 kilo thruster, provided that you have, of course, all the other subsystem in good shape to do this. I don't have an Excel file or something here in front of me, but I think that the propellant mass fraction will be very, very high. So I think that the higher specific impulse is necessary, but I mean, it's just my first feeling. Of course, I'm happy to hear what the others are going to say about this.
For us, it would be the holy grail of thruster, because you can do everywhere. You can go everywhere in the solar system, back and forth.
Ah, yes.
Would be
for sure.
Really amazing.
Okay, apart this very long-term, let's say, development or roadmap that we could face. In the short term, I think there are some challenges, as has been already pointed out by many speakers, to be faced. So there are some themes that have been that arose now in this discussion. First of all, so we need to improve performances in different directions. There is an issue regarding the cost. Cost reduction. How is important in your because of course for commercial application is maybe the driving factor, but for other kind of mission is not could be not the main driver for a selection. But I think we need also to ensure a certain reliability of our systems, especially if we plan, as Sabrina also shows in her presentation, if we want to use this system in very complex missions, interacting with other systems that are, of course, that can introduce safety requirements, very that is important to, of course, to fulfill. So, which is speaking of reliability, for example, and that in many cases is which is your feeling on this? How far we are from a reliable system that can be used in this kind of missions, and what we need to improve it? Because speaking of CubeSat propulsion, there are some cases when the ACSS are not fully applicable, but of course this should be considered in other kind of missions. Which is your feeling, Daniele, or of course all the others that can interrupt in any moment? So a reliability of a propulsion system that should be used in complex missions. How can we improve this aspect?
Well, I think that the difficult come from the compromise between cost and reliability required. I mean, everybody knows that it's possible to make a very reliable propulsion system if you don't have a limit on cost, and of course you have some you have to introduce some limitation in mass and volume, but especially cost. If cost is not a problem, electric propulsion system are already flying and are very reliable. So I think that the effort which I believe is needed from the agency is to, and I still it seems to me that there are still some problem in the approach. The old approach was let's use a CSS, let's use the standard that has been used till now, and of course they work, but they provide a certain amount of cost. If you wanted to reduce cost, you have to change the standard. So the real challenge is to define a new standard that are good enough for what is needed. So if you ask me from an engineering point of view, I believe it's for sure possible. The problem is to identify what is the best trade-off, what is the correct trade-off between the cost and reliability. And this is an open question. For example, you know better than me about the use of COTS component. They drastically reduce cost, but they open questions about how reliable they are. And the point is that this is a big challenge that I believe should be faced by agencies.
Yes, and of course there are a lot of discussion ongoing in this perspective, and how ground testing can improve also this the reliability of a system. Of course, not dealing with the electronics as Daniele pointed out regarding COTS. Of course, that is a general problem, not only for electric propulsion but for all the other subsystems. How the testing on ground are representative of the flight conditions in terms of reliability of the system. When I say reliability, I see, of course, all the capability to really understand which is the behavior, the correct behavior of the propulsion systems. Francesco, do you have some experience in this regarding how testing can on-ground testing?
I can say that the test and validation processes should be better documented, and we need something formal we need a standardization process of the test activities, and then with the next missions with the data from flight data, we can compare the data with the test activities, and in order to improve the reliability of the testing activities, and also to decrease the number of hours needed for the qualification. So this could help in order to decrease the cost of the development of an electric thruster. And so I need that it's particularly important also for the performance parameter to have a direct comparison between what we see in orbit, but we don't have experience in CIRA, and what we see in the facility. We know certainly that the vacuum level that given by the pumping system is particularly important. So we are investing a lot on this kind of subsystem of the facility. But I think that is important on one side, the standardization of the testing. On the other side, comparison with the mission, and so in orbit data.
Okay, and in terms of let's say in orbit testing, of course we have on ground measurement capabilities, so we can see probably all details of the propulsion system. On the other side, in orbit, maybe we could have only aggregate measurement, because we can measure the effects of electric propulsion on the systems on our satellites in terms of changing orbit, or on this perspective, there could be some new challenges also coming from the need for in-orbit experimentation, in-orbit testing, regarding what we need to measure in orbit respect to what we are able now to measure on ground. I don't know if the question is.
I don't know if anyone else wants to answer. Of course, this is a delicate issue because we know that on ground we can have a thorough characterization of the thruster, while in orbit we have discussed it also with you, with the Italian Space Agency several times, that we have a restricted number of parameters that we can monitor in orbit to check the health status of our propulsion system. It's true that at least in low Earth orbit, I believe that this is very important because reliability, to me, is becoming the most important factor, comparable with cost. Because in the end, if we will put in orbit, in low Earth orbit, a number of satellites which are not extremely reliable, we will end up polluting the space around us, and that will be an unbearable cost for the future. So reliability is certainly a parameter that has to be addressed very carefully. On ground, what we can do is to test as much as possible, over-test everything in order to make sure that we have a certain margin. On orbit, this is something that can be discussed, of course, but we have limited capabilities of monitoring and, of course, of intervention. It has to be said that now there are about 2,000 satellites that have been launched in the last 2 years by SpaceX, Starlink Constellation, and by OneWeb, using whole thruster electric propulsion. So this is already a good situation to monitor continuously in order to see what is the reliability of systems similar to the ones that we are developing. And up to now, the result is pretty good. I think that almost all of them are working successfully. A few units maybe not, but in general. I'm currently monitoring them to see if the satellites that they launched are raised to the final orbit or not. And actually, the success rate is quite good. It's almost 100%.
Okay, thanks a lot, Tommaso. So as we said, as we saw, of course, there are a lot of different missions that could be enabled by electric propulsion. There are already some example in LEO orbit, in GEO, in space transportation also is another possible application. Speaking of space tags, for example, for high propulsion, space exploration, as announced, as highlighted also by Francesco. And each of them probably require a specific kind of a technology of electric propulsion with some requirements and some performances. Which is in your, just to conclude this discussion today, is it possible to identify, in your opinion, an application where the electric propulsion can be a game changer technology as compared with the traditional technology or chemical, for example? So if you need to choose among all these kind of application, is it possible to define, to see which is the best or not? Or no, we are not yet in this condition. Just to provoke a little bit. I see Tommaso laughing.
Actually, electric propulsion is my own field of operations, so I would say that every mission that you mentioned is, of course, a relevant application for electric propulsion. I'm not saying this just because I'm an electric propulsion expert. I'm saying this because I think that at different level, all these missions can strongly benefit from electric propulsion. Of course, space exploration, when the delta V is very high, not hundreds of kilometers per second at the moment, but already close to 10 kilometers per second, well, there probably we are necessarily bound to use electric propulsion. For the other missions in low Earth orbit and geostationary orbit, it is largely used. Basically, it's the baseline for most of the constellation satellites and even geostationary platforms that use electric propulsion for station keeping, but nowadays almost always also for orbit raising. So it's difficult to make a choice for me, but maybe I'm too biased or too involved, so I leave the floor to the others.
Francesco, please.
Yes, I want to answer your question by not answering your question. So you have asked for a game changer in the field of propulsion, but I want to share the experience that I have in the overall field of guidance, navigation, and control, which involves low thrust propulsion, electric propulsion in the deep space. We are in the framework of the ERC-funded project Extrema. We want to forge deep space CubeSats which are able to travel in a totally autonomous way without any human intervention. This is very important for us, or at least for people that do GNC, because it means that you don't have to operate the spacecraft when it's in deep space cruise, which can take hundreds of days, if not years. So in this context, we want to make what we call self-driving interplanetary CubeSat by using the self-driving word that is very trendy now in automotive. And in this context, we are conducting basic research for what concerns autonomous navigation, so the possibility of a spacecraft to determine in autonomy its position, and autonomous guidance and control, the capability of the spacecraft to determine the path to follow in the future and to enforce it by virtue of its own primary propulsion. Now, this means that the thruster is let's say, a user of our technology, but it means that we are thinking of this kind of machines which are able to travel in the deep space in a totally autonomous fashion, which requires, in my case, miniaturized, but in general, electric thrusters able to be, let's say, reliable, to cope with this kind of technology, and to match with this autonomous GNC chain properly. As I said, this doesn't answer your question, but it's a very important milestone for people that use electric propulsion and are not developers like me.
Yeah, thanks. I think this interaction, of course, is crucial now for the success of a future mission, because we have a requirement from one side and we have the developer on the other side, and of course we need to interact each other. So absolutely, thanks, Francesco, for your for what you just said. I don't know, Marco, we are a little bit out of time. We could even continue for hours, I think, with our speaker. Let me know if, please.
If you want to make a final remark, then I think we can wrap up with the conclusions.
Yeah, I think first of all, I would like to thank the speaker for this discussion, and maybe many others will follow in the future. This kind of event is, I think, is important even to discuss with the community on different perspective, as also Francesco highlighted. Just a final remark, of course, electric propulsion is one of key technology addressed by ASI, but also at European level. And just to inform the community that within the EPIC project and funded by European Commission, there will be the definition of the roadmap for electric propulsion. In the we will start the consultation with the community just after the summer break. So even the let's say the outcome of the present talk, I think it could be represent a very good input for that exercise that we are going to perform in order to, of course, feed the call on electric propulsion within the Horizon Europe program. So I think probably if I have to summarize with just one word, the talk, we need in-flight demonstration for electric propulsion. And mostly we need to compare, we need to correlate ground testing. We have a lot of capabilities in Italy at the ESA level, as Sabrina also highlighted. We need to correlate the test with the in-flight measurement. So we have a lot of work to do on this, and we are ready to do it. I'm sure. Thanks, Marco. The floor is yours.
Thank you very much, Marco Di Clemente, head of the technology unit at the Italian Space Agency, and thank you to all the panelists for having shared with us these ideas. I think it has been an extremely dense workshop. I just want to wrap up, in addition to thanking Italian Space Agency, European Space Agency, and all the presenters and the panelists. I would like to wrap up recollecting the few keywords that have been repeated more and more times, both coming from university, from the industry, and also supported by the agency. The aim of this workshop was to see what happens when plasma physics encounters celestial mechanics. And we have seen that this mix is extremely appealing and has a lot of potential for new missions development. Now, really the key word that has been summarized by Marco Di Clemente, that is in-flight demonstration, is the common ground on which we need to build our future capability. We need to have operations. The only possibility to see what is this combination of plasma physics with celestial mechanics is to be in real space. An end-to-end test of an electric propulsion system, and in particular of an all-electric satellite, is not possible on ground. So this is why both at the university, at the research center, at the industry, we are eager to flight test our devices. T4I is waiting for the switch on time. At CTIL, we are very much excited about our next coming launch with Virgin Orbit of our technology in a few months from now. Now, this is the playground, let me call it this way, the playground where we need to make operational experience. Then we have understood that the trade-off between miniaturization, cost, and reliability is a continuous balance that we need to adapt to according to the customer needs. So we will have A-class propulsion systems. We will have commercial-grade propulsion systems. But back to the previous playground, we need to be able to test all of these in their relevant environment. We have understood that the game-changing provided by electric propulsion is not only opening new possibilities of sailing through the solar system, arriving to new shores, but is also crucial for a sustainable use, as we have seen in the presentation of Camila Colombo and of Sabrina Copino, in the near-Earth environment, which means that we are able to deploy satellite constellations. That is another word that is coming and coming, but most important, to deorbit at the right time and in the right place of the satellites, and to enable collision avoidance maneuver. Thank you, Sabrina, for your personal, for being a personal witness of this scary environment where we need to live and work with now. And then we have seen these capabilities that we have at the research center like CIRA, that is simulating both numerically and experimentally all that is related to electric propulsion. And finally, Francesco has brought us to these new perspectives. And I really would like to take the challenge that he has given, because of course this workshop is just the initial step of a longer story. So we have the challenge of this 100 km per second velocity that remains as a challenge. We have understood that the technology now is not ready to do that, but I'm sure that merging our efforts and ingenuity, this is something for sure the youngest students of all of you from university world will be able to design, conceive, and make possible in real life. Thank you very much for this very fruitful discussion, and hope this is going to be the first one of a series, because it has certainly opened our mind and our perspective toward future. Thanks a lot, and bye-bye.
Thank you.
Ciao,
And,
ciao.
Bye.
thank you, and thank you
Bye-bye.
again for.
Thank you
Thank
very
you.
much.
Bye.
Bye. Bye-bye.
Goodbye,
Thanks a lot.
everybody.
Bye-bye.
Ciao, ciao.
Ciao a tutti, grazie.
Ciao.
Bye.